The universe is going to end. Probably. This is Greg, and Greg has just learned this information. Calm down, Greg. Most of these won't happen for a long time, like a really long time. But one of them could technically happen without any warning. Physicists have several ideas for how everything might end, like the universe could just freeze out of nowhere, collapse, tear itself apart, or the laws of physics could simply flip. And the annoying part is, which ending we get depends on something that makes up most of the energy of the universe. And something that we still don't properly understand, kinda like a wheel of fortune that spins forever with question marks everywhere, with the unknown variable being dark energy. Which sounds very scientific, but it is basically human terms for we can see what it's doing, but we don't know what the hell it is. And depending on what dark energy actually does, our universal wheel of fortune gets a different ending. So let's start with the ending our standard picture of cosmology has traditionally pointed towards. Heat death. This is coffee. Coffee hot. This is Greg. Greg also hot. Different problem. The coffee is hotter than the room around it, so heat moves from the coffee into the room. Eventually, the coffee cools down. In return, the room gets an incredibly tiny amount warmer, and everything moves closer towards reaching the same temperature. This is the basic problem facing the entire universe. Energy spreads out. Stars burn fuel. Light travels through space. Things collide. Things decay. And over enough time, usable energy becomes more and more spread out. A property known as entropy. Entropy is one of those words that make a simple idea sound like you need a master's degree to understand it. But let's make it simpler. This is Greg's bedroom. Monday, everything is organized. Greg knows where his socks are. Now, we allow Greg to exist naturally for a few days. Friday, the same room. There are 17 plates on the floor. Due to budget cuts, we can only see 2. One sock is on the ceiling. We do not know how it got there. Neither does Greg. There are far more ways for Greg's room to be messy than perfectly organized. That is not a complete definition of entropy, but it gives us the useful part. Over time, energy tends to become more and more spread out, and the universe has a lot of time. So we wait. 1,000,000 years pass by. Then 1 billion, 10 billion, 1 trillion. Stars slowly run out of fuel. New stars become harder to form. Eventually, the era of ordinary star formation ends. The universe slowly gets darker. White dwarfs cool. Neutron stars remain, and black holes become some of the last major objects left. But even black holes may not last forever. According to Hawking's calculations, black holes slowly lose energy through something called as Hawking radiation. For a black hole roughly the mass of our sun, evaporation would take around 10 to the power of 67 years. That's the number 1 followed by 67 zeros. This number is stupidly large. The universe is currently about 13.8 billion years old. That's roughly this much. And larger black holes last even longer, potentially approaching timescales of around a googol years for the biggest future black holes. That's 1 followed by 100 zeros. Greg wants to count them. We'll come back to him. Eventually, the black holes you see in this picture will evaporate. The great lights of the universe are gone. Usable energy has become incredibly spread out. There are no meaningful temperature differences left to exploit. Nothing has enough free energy to keep doing interesting things forever. Time hasn't necessarily stopped. There's just nothing left to happen. The universe doesn't explode. It doesn't collapse. It just slowly runs out of things to do. Entropy makes it such that there is no energy difference between any 2 points anywhere in the universe. It's just cold and empty forever. Probably the most boring apocalypse imaginable. But heat death assumes the expansion of the universe keeps behaving roughly the way our standard cosmological model expects. But what if dark energy gets stronger? Because then the universe doesn't slowly even out and fade away. It gets ripped apart. The Big Rip. Right now, the universe is expanding, and the expansion is accelerating. In our standard model, dark energy behaves roughly like a constant property of empty space. But there is a hypothetical possibility called phantom energy. We gave the hypothetical universe destroying energy a ghost name. If this kind of energy exists, the dark energy density increases and the effect driving expansion could become strong enough to overpower structures that are currently held together. At first, galaxy clusters would separate. Then galaxies themselves could be torn apart, then followed by star systems. And eventually the Earth loses the Sun. Greg loses his landlord. Greg briefly starts supporting the Big Rip, and then Earth is torn apart. Greg is reconsidering his life choices. As expansion becomes even more extreme, molecules could be pulled apart, and in the last dying moments, even atoms and subatomic particles. And in the classic Big Rip picture, the universe reaches a future singularity after a finite amount of time. One famous model put the end roughly 22 billion years into the future. That's way less than 10 to the power 100 years. But that number depends on phantom energy actually being real. We don't know that it is, but we also don't know that it isn't. And this is where things have recently become more interesting. Observations from Decay have strengthened hints that dark energy may change over cosmic time. This is not a discovery yet, but if dark energy isn't constant, predicting the end of the universe becomes considerably more annoying. Maybe expansion keeps accelerating, maybe it tears everything apart, or maybe dark energy weakens enough for gravity to make a comeback. And gravity has been waiting. The Big Crunch. This is the universe expanding. Now imagine it slows down. Slower, slower, and stops. For one moment, the expansion of the universe has reached the top of the hill. Greg has also reached the top of a hill. Greg forgot why he climbed it. And then gravity starts pulling everything back. The universe begins contracting. Galaxy clusters approach each other. Galaxies collide more often. Space becomes denser, and the universe starts getting hotter. Basically, the Big Bang, but in reverse. As space contracts, radiation becomes more and more energetic. The universe becomes increasingly hot and dense. Eventually, planets would be cooked by the surrounding radiation. Greg has applied SPF 50+++ sunscreen. The collapsing universe is several billion degrees. Even sunscreen has limitations. Stars collide, black holes merge. Matter is compressed into an increasingly dense state, and eventually we will reach conditions where our current understanding of physics is not enough. The universe collapses toward an extreme final state, the Big Crunch. The problem is that the universe currently appears to be accelerating outward, not slowing down. So a simple Big Crunch does not fit the standard picture very well. But if dark energy evolves, or our cosmological model is missing something, a future reversal becomes a question worth asking. And if the universe collapses, there's another question. Does it actually stop? The Big Bounce. Greg has a ball. Greg drops the ball. The ball hits the floor and bounces. Greg has solved quantum gravity. No, he hasn't. But the basic idea behind a big bounce is that the Big Bang may not have been the absolute beginning. Maybe a previous universe existed before ours. It expanded, contracted, reached an incredibly dense state, and instead of becoming an infinite singularity, some unknown physics stopped the collapse. And then, bounce. New universe. New Greg. The Big Bounce appears in several speculative cosmological models. But we have a problem. Gravity is described extremely well by general relativity. Tiny particles are described extremely well by quantum mechanics. But when you take an entire universe, crush it into an absurdly tiny state, and ask both theories to work together, things get complicated. We still don't have a complete, experimentally confirmed theory of quantum gravity, so the Big Bounce still remains speculative. But at least the universe survives, kind of. The next ending doesn't give it that option, because the universe may be sitting in the wrong vacuum. Not that vacuum. Vacuum decay. This is empty space. Looks empty. Quantum physics disagrees. In modern physics, fields exist throughout space, and those fields can have different energy states. Greg has a ball again. Greg puts the ball here. The ball looks stable. Push it slightly and it comes back. Stable. Except there's a deeper valley down there. The ball isn't in the lowest possible state. It's just trapped in a state that is stable enough. This is a false vacuum, and there is a serious possibility based on the measured properties of particles such as the Higgs boson and top quark that our current vacuum may be metastable. A metastable state is a quasi-stable condition where a system temporarily resists transitioning into its lowest possible energy state, kinda like here. To be very clear, this does not mean vacuum decay is expected tomorrow. Calculations generally give our vacuum an absurdly long lifetime if the standard model remains valid to extreme energies, and unknown physics could change the entire picture. But hypothetically, a tiny region of space could transition into a lower energy vacuum state via bubble nucleation. A bubble forms. Inside that bubble, the fundamental condition that allows particles and forces to behave the way they do may be different. Maybe atoms as we know them cannot exist. Maybe chemistry doesn't work the same way. The honest answer is that our familiar physics would no longer describe the vacuum in the same way. And then the bubble expands very quickly at effectively the speed limit set by relativity. Here is Earth. By the time light carrying any warning of the event reaches Earth, no alarm, no telescope warning, no final speech. The conditions allowing Greg to exist simply stop applying. For the first time in this video, Greg does not come back. Anyway, this is hypothetical. We have never observed vacuum decay, and the exact stability of our vacuum depends on extremely precise particle measurements and on whether physics exists beyond the standard model. So, Greg's helmet will not help, but neither will taking it off. There is, however, one more possibility. Maybe the universe never has a final moment at all. We usually imagine an ending as an event. Something explodes, something collapses. Netflix cancels a good show after their first season. There is a final moment. But the universe may not work like that. If expansion continues forever, time may simply continue, and continue, and continue. Stars still die. Black holes may still evaporate. The universe would still become cold and empty. But there may never be a specific second where the universe officially ends. It just becomes increasingly uneventful. Because over enormous or infinite timescales, cosmology starts asking some deeply stupid sounding questions that are unfortunately mathematically serious. For example, Boltzmann Brains. Imagine an extremely rare random fluctuation produces a temporary structure. Now, imagine by an incomprehensibly smaller probability, these particles briefly form something capable of having a conscious experience. A brain floating in empty space, possibly complete with false memories of a life it never lived. This is called a Boltzmann brain. Greg has met the brain. The brain thinks Greg is a hallucination. Greg thinks that the brain is Dave. Forget that. The point isn't that scientists expect floating brains to start appearing next Tuesday. But Boltzmann brains are a problem that appear in some cosmological models when we extend probability across absurd timescales. Sometimes the weird consequences of a model tell us we may be asking the wrong question, using the wrong assumptions, or missing a part of the physics. So, how does the universe end? The boring answer is, we still don't know. If dark energy behaves like a cosmological constant and accelerated expansion continues indefinitely, the universe heads towards a cold, dilute future. Heat death. If some phantom form of dark energy drives increasingly extreme expansion, the big rip. If expansion somehow reverses, the big crunch. If new physics prevents a final singularity and produces another expansion, maybe a big bounce. And if our vacuum is metastable, vacuum decay remains one of the strangest possibilities physics allows us to discuss. But right now, Dark energy has made the story more interesting. Results from the Dark Energy Spectroscopic Instrument, Decay, have strengthened hints that dark energy may evolve over time. The evidence has not reached the level physicists required to call it a discovery. But if the hint survives future observations, one of the biggest assumptions in our standard model of cosmology may need to change, which means humanity has spent centuries studying the sky, built telescopes, launched satellites, developed general relativity, invented quantum mechanics, mapped millions of galaxies, all to answer the question, how does everything end? And our current answer is, probably gets cold. Maybe. Greg has a different theory. Greg believes the universe will end in 2037. Why, you ask? Well, he saw it on TikTok. And the only way to stop it ending in 2037 is by subscribing. Thank you, Greg. If you want to know what the universe is actually made of, that's a much worse rabbit hole. Maybe I'll explain every fundamental particle next. Probably.